Hello, everyone, and welcome back. This is video 2 of the Materials 2DO3 Thermodynamic Properties of Alloys and Phase Diagrams exam review. My name is Josh. I'm a second-year materials engineering student from the University of McMaster. And today in this video, we're going to be going over non-ideal solution properties. So without further ado, let's get into things. So it's important to know that there's something very important that non-ideal solutions use. So for non-ideal, I'm just going to use this NID, non-ideal. Non-ideal solutions, they use an activity coefficient. The activity coefficient describes how ideal our solution behaves. If our activity coefficient is equal to 1, our solution is ideal. If our activity coefficient is greater than 1, our solution exhibits positive deviation. And if our activity coefficient is less than 1, our solution exhibits negative deviation. Now, how do we find our activity coefficient? It's just the mole, not the mole fraction. First, it's the activity divided by the mole fraction that is equal to our activity coefficient. This is super important to note when we're dealing with non-ideal solutions. Something super important about non-ideal solutions is that their enthalpy of mixing is not equal to 0. Why? Well, let's go through the math first. Before we even get into the math, we know that as temperature increases, any kind of solution is going to tend towards ideality. Meaning, as we increase our temperature, what happens to our activity coefficient? Our activity coefficient approaches 1. All right. Now, with that being said, let's get into this enthalpy derivation. So we're going to set it up just like before. The derivative of Gibbs free energy, we'll do molar Gibbs free energy of mixing from A divided by temperature, taking the derivative of that with respect to temperature, is equal to the partial molar enthalpy divided by T squared. Okay. Now, before we even get into things, what we can do to make this look a little bit nicer, because I don't like, this kind of looks ugly to me. We know that the derivative of 1 over T is just equal to negative dt over T squared. So right away, we can just kind of make this look a little bit better by just saying this is the derivative of 1 over T, and we're just equating that to the enthalpy of mixing, just like that. Now let's get down to things. So in non-ideal solutions, our Gibbs free energy term, our molar Gibbs free energy of mixing, is equal to RT ln of the activity of A. Now, what's the activity of A? The activity of A is equal to our activity coefficient multiplied by our mole fraction. In other words, our partial molar of A is equal to RT, ln of our activity coefficient, plus ln of our mole fraction. If we divide our Gibbs by T, we get this. If we're to now consider derivatives, we know that XA does not rely on T at all. But we know that our activity coefficient does rely on T. So instead of taking our derivative with respect to our Gibbs free energy now, we can just replace this by the Gibbs free energy of R ln activity of A with respect to 1 over T is equal to the enthalpy. And this is a term, not gamma. Okay, so what this shows is that our R ln of our activity coefficient is proportional to 1 over our temperature. What this means is as we increase our temperature, our R ln gamma term is going to decrease. We can even take this R out. Ln of gamma is proportional to the inverse of our temperature. So as we increase our T, this term here is going to get closer and closer and closer to 0. Or as we increase our T, this term is going to get closer and closer and closer to what makes the natural logarithm 0, 1. Meaning, this is the kicker, as our temperature increases, what happens to our activity coefficient? It approaches 1. So what happens to our solution? It approaches ideality. Pretty cool when you lay out all the steps. So what can also be done is I like to think of it as this. R ln of our activity coefficient is equal to a function of 1 over T, and that function can be equal to H over T. So let's write it out. So it's set in stone. As our temperature increases, our ln of the activity approaches 0. Therefore, our activity coefficient approaches 1. If we are to have positive deviation, we're going to have weak AB bonds. This is going to cause the like bonds to cluster. When we have positive deviation, what happens to our gamma? Our gamma is greater than 1. This is going to give us a positive slope in terms of enthalpy. So we're going to have a positive enthalpy. For negative deviation, we have strong AB bonds. So we're going to have ordering, meaning there's going to be ordered phases. Our activity coefficient is less than 1, meaning our slope is negative. So we're going to have negative enthalpy. This is exothermic, and this is endothermic. Cool. Now, how are we going to determine our activity coefficients? This is something that can be a little bit difficult. determining the activity coefficients of, let's say, A, if we have the activity coefficient of B. Now, if you were in class, there was a lengthy derivation of this, where we started with talking just purely about activities, and then we found out that if we were to graph the logarithm, log base 10 of our activities, we'd get this weird graph that both ends go off to infinity, and we couldn't gain any value from this. Now, instead, when we graph this same thing in terms of our activity coefficient, it's a lot nicer. So it's going to go off to infinity on the y-axis, and it's going to taper off, and it's going to have an intercept point on the x-axis. The x-axis, we'll say, is the logarithm of gamma b, and the y-axis is going to be xa over xb. So we know that the derivative of logarithm gamma a is going to be equal to our integral here of x. I flip these. This should be b. This should be a. xb over xa d log of gamma b. Now, I don't know how to integrate that. So what we're going to do is we're going to look at the different shapes that we can make and calculate the area underneath the graph at every single point. And sorry, this should be negative. The first bound is log gamma b when xa is equal to 1. When xa is equal to 1, xb is equal to 0. So where is our log on the x-axis? It's right here. Our second one is going to be log gamma b at any arbitrary point. xa is equal to xa. Let's say our xa we want is right here. We are the log of the activity coefficient of A is the area underneath this graph here. We would calculate the area, we would raise that area to the power of 10, and that would give us the activity coefficient of A. From there, we can do different things to find out the activity. With that all being said, that's all there is to it. It might sound like a lot, but in the end, it's hard, but you can get it. If we were to take the second one, another points, we would have to sum up both of these areas. So we would add this one to be a triangle. We calculate this second area, this one, by doing a trapezoidal calculation. This is our trapezoid. Just using geometry for that. All right. One last thing about just our arbitrary non-ideal solutions. Their Gibbs free energy term consists of two different terms. A Gibbs free energy excess term and a Gibbs free energy ideal term. The Gibbs free energy ideal term is always, always, always going to be the same. Let's talk about our partial molar Gibbs free energy. So our partial molar Gibbs free energy has our excess Gibbs and our ideal Gibbs. Our ideal Gibbs is always, always, always going to be RT ln XA. That is the partial molar Gibbs free energy of an ideal mixture. Now for our excess term, you can take a guess what that's going to be. It's going to be RT ln of our activity coefficient of A. If we're to use logarithm properties, this is just equal to RT ln of the activity, right? We know this is the Gibbs free energy. Okay. Before we get into the fun stuff, which is the phase diagrams, we have one last thing to tackle. This is going to complete our tool belts, our toolbox of everything that we're going to need in order to analyze phase diagrams. And that being regular solutions. Okay. Regular solutions. So there's a couple special properties to regular solutions. Regular solutions are a kind of non-ideal solution. They do not, they're not ideal solutions. So what do we know about non-ideal solutions? They have an enthalpy of mixing that is not equal to 0. The thing that's interesting about regular solutions now is their entropy of mixing is equal to their ideal counterpart, which is negative R times the sum of XA ln XA. Now, what do we know about the Gibbs free energy of any non-ideal solution? Well, it's equal to RT, ln of the activity. And it's equal to an excess term plus an ideal term. If we split up the natural logarithm, we get our excess term and our ideal term. Just like that. Now, there's one important property that we're given as part of regular solutions. And that's the ln of our activity coefficient of A is equal to this alpha term multiplied by our XB term squared. Or the ln of the activity of B is equal to an alpha term times our XA term squared. Hopefully this isn't anything too confusing for you. Now, what you might be asking to yourself is, where does this stuff come from? Where did these two new terms come from? Well, I'll explain it to you. We're going to start off by defining the partial molar enthalpy of B to just be equal to RT alpha multiplied by XA squared. And we're going to get our partial molar A to be equal to RT alpha XB squared. Now, let's find the molar Gibbs free energy of A. We know that's equal to RT. We'll put in RT first. Ln gamma A plus ln XA. We know that this is also equal to the partial molar enthalpy of A plus T times the partial molar enthalpy. Sorry, not plus. That would have been bad. Minus T times the partial molar enthalpy of S. We know that the partial molar enthalpy of S is just equal to the ideal case. So we're going to have minus T times minus R ln XA. And on the right side, we have the same thing. Now look at this. The two negatives turn into a plus, and they're going to cancel out this term. So what do we have now? RT ln activity coefficient of A is equal to the partial molar enthalpy of A. Well, what do we know the partial molar enthalpy of A being equal to? Well, we know that's RT times alpha XB squared. Canceling out the RTs, 1 gamma A is equal to alpha XB squared. And you can do the same thing with the other one, the B term. You can do the same thing for it. Okay. So now we know our Gibbs free energy for our excess term of A, right? That's equal to our partial molar enthalpy of A, which is equal to RT ln gamma. I'm going to leave an extra term, and that's just equal to alpha XB squared. The thing about alpha is constant in a regular solution, no matter what temperature you're at. Let's get this. Okay, now let's put two different temperatures in. We know that if we have T1, we're going to have a gamma at T1. And we know that enthalpy is equal to alpha XB squared. Now, if we were to change the temperature, our gamma would change. But if we keep the composition of the same, that's also going to be the same for this. So what we can do is say now T1 over T2 is going to be equal to ln gamma at T2 divided by ln of gamma at T1. There's a relationship between gammas at different temperatures due to the alpha term being constant. Sorry, and if we're talking about enthalpy, I should have put RT here. Okay. Now we're going to see, well, where does this alpha thing come from? What's happening there? And to do that, we're going to use a statistical model. I believe it was the quasi-chemical model. This statistical model is going to show us where our alpha comes from. We're going to make a couple major assumptions. Our assumptions are going to be the molar volume of mixing is 0. We're going to assume bonds are only affected neighbor atoms. So my bonds are only affecting my immediate neighbors. They're not affecting anybody to my diagonals. And our energy is equal to our bond energy, which are less than 0. Okay. So let's start off with something simple. The energy of our mixture is going to be equal to the number of AA bonds times the energy of each AA bond plus the number of BB bonds times the energy of each BB bond plus the number of AB bonds times the energy of each AB bond, right? We're having our total energy times the total number of bonds. Now, if we are trying to consider this in a different way, we can say the number of A atoms times the coordination number of our lattice. This is going to give us each atom. Our coordination number is going to consider each bond. This is equal to the number of AB bonds, right? Because each AB bond considers one A bond, plus 2 times AA bonds, because all of our AA bonds consider two A bonds. The bond coming from this A and the bond coming from this A. They're both interacting. This gives us that our AA bonds are going to be equal to half of this term minus that term. Not bad. The same thing can be said for B. Now, if we now place this term here in place of PAA and PBB, our energy is going to be equal to 1/2 and a coordination number, EAA, plus 1/2 and B coordination number, EBB, plus the number of AB bonds multiplied by the total energy of the AB bonds minus half of EAA plus EBB, which is just the average like bond energy. Now, let's consider the energy of our unmixed. Energy of our unmixed is going to be equal to simply that. If we were to take our E of our mixture and minus our energy of our unmixed, the change in energy due to mixing is simply going to be equal to the number of AB bonds times the energy of the AB bonds minus the average energy of our like bonds. What can be said about this? Well, think of our ideal solutions. If we say that our energy is just equal to our enthalpy of mixing, right? Because that is what we are doing. We can say now that in ideal mixtures, the energy of our AB bonds is just equal to the average of the energy of our like bonds. That is exactly what an ideal scenario is saying. So let's think now. Let's think in terms of non-ideal scenarios. We know that if our enthalpy is less than 1, this means, sorry, not less than 1, less than 0. Our activity coefficient is less than 1, and it's exothermic. Since these things here are negative, if our energy of the AB bonds are less than the average like energy, this is going to give us our negative value. So this means the energy of the AB bonds are larger than the energy of like bonds, and vice versa. If we have a positive enthalpy, we have a activity coefficient greater than 1, so our AB bonds are going to be less than the energy of our like bonds. Now let's consider the probability of each neighboring lattice site being occupied by each atom. So if we have this circle please, there we go, being site 1, copy that, oops. This one being site 2. And every time I draw an arrow, it's going to be a multiplication symbol. Site A has XA and XB probability of being occupied by A or occupied by B. If there's a 99% of B, there's a 99% chance of the site atom being occupied by B. The same thing for site 2. It can be occupied by XA or XB. Now, let's try to find the probability of what these two sites are going to be? Well, both of them can be XA, both of them can be XB. One can have A and one can have B, or one can have B and one can have A. Altogether, this is going to give us XA squared plus XB squared plus 2 XA/XB. And we know this equation has to be equal to 1 because the probability of both lattice sites being occupied must be equal to 1, or else there's a major issue. So now, the number of AB bonds is going to be equal to half, because we are associating this with pairs now, half of the total number of molecules, or total number of atoms, times the coordination number, multiplied by the probability of both lattice sites being occupied, or the probability of the lattice site being occupied by A and B at the same time, which is this. So in total, we get this. Plugging that into our equation now, we get a brand new term. Now we're going to do something fancy with this brand new term. We're going to say, okay, this is a lot of stuff, and we can extract a lot of this stuff very easily. So everything that I've just drawn in blue, we're going to name a new variable, omega. So enthalpy of mixing is going to be equal to omega XA XB. And we know that the enthalpy of mixing is also equal to RT alpha XA XB. So what can we say? Well, we know there's a relationship between alpha and omega. Omega over RT is equal to alpha. Omega, we can call our interaction parameter. It measures how well our atoms interact with each other. All right. From there, we talked a little bit about subregular solutions. Subregular solutions don't have that perfect parabola from XA and XB. They have a little bit of a cubic function instead. You should just know that. So our regular solutions, they're going to be having an enthalpy of mixing of omega. If we were to say XA times XB, we're going to say XB is XA, so 1 minus XA, sorry. You can see that we're going to end up multiplying XA by XA, which is going to give us a parabola if we were to have XA being the x-axis. Subregular solution is going to have a term in front being like A plus B times XB times 1 minus XB, which is XA, multiplied by XB. And you can see here, somewhere along the way, we're going to end up getting a cubic function. All right, that's all I wanted to talk about for this video. Hopefully you enjoyed. Hopefully you understand this stuff a little bit more. Try to go through this video slowly. If you don't, comment below if you have any questions. And in the next video, we're going to be going over some fun stuff about phase diagrams, and we're going to be chopping up that final part into multiple small parts so you can really get down and understand it. Thanks for watching, and I'll see y'all later.